Ever wondered how AI systems like GPT or BERT achieve such human-like language understanding? The answer lies in a revolutionary architecture that's redefining machine learning, the transformer. Today, we're diving deep into the technical heart of transformers, how they process data, why they outperform older models, and the mathematical principles that make them work. Buckle up, because this is the inside story of one of AI's most impactful innovations. Before transformers, recurrent neural networks (RNNs) and convolutional neural networks (CNNs) dominated sequence modeling. But they had critical limitations. RNNs struggled with long-range dependencies due to vanishing gradients, while CNNs relied on fixed receptive fields that couldn't capture global context. Imagine trying to understand a paragraph where each word's meaning depends on something mentioned 5 sentences back. Traditional models floundered here. This gap set the stage for a paradigm shift. In 2017, Google's research team introduced the transformer paper, "Attention is all you need," their key insight. Replace recurrent layers with self-attention mechanisms, allowing models to weigh relationships between all elements in a sequence simultaneously. This wasn't just an improvement, it was a fundamental rethinking of how models process information. Let's break down the core components. Self-attention works by computing 3 vectors for each token: queries, keys, and values. Think of queries as what I'm looking for, keys as what I can find, and values as the actual data. The model calculates a score for each query key pair, normalizes it with softmax, and multiplies by the corresponding value. The result? A weighted sum that captures contextual relationships. For example, in "the cat sat on the mat," the word cat might attend strongly to sat, and mat to understand the action and location. But wait, how does the model know the order of tokens? Unlike RNNs, transformers don't process sequences sequentially. To encode position, they use sinusoidal functions or learnable embeddings. These positional encodings add information about each token's place in the sequence, enabling the model to distinguish between "I saw the man with the telescope" and "I saw the man with the telescope." Yes, ambiguity matters here. The formula for positional encoding involves sine and cosine functions of different frequencies, ensuring unique representations for each position. Transformers don't stop at one attention mechanism. They use multiple attention heads, each focusing on different aspects of the data. For instance, one head might capture syntactic relationships, while another identifies semantic roles. These heads are concatenated and linearly transformed, allowing the model to learn diverse patterns. This parallel processing is why transformers scale so effectively. More heads mean more capacity to model complex dependencies. After attention, each token passes through a feed-forward network (FFN), a simple 2-layer MLP. But here's the trick. The FFN is applied independently to each token, preserving parallelism. To stabilize training, transformers use layer normalization, which standardizes the inputs across the batch. This prevents exploding gradients and accelerates convergence, critical for training deep models. Transformers are trained using a masked language model, MLM, objective. Randomly, 15% of tokens are replaced with a token, and the model predicts them. But here's the catch. 80% of the time it's replaced with, 10% with a random token, and 10% left as is. This forces the model to learn context from surrounding words, not just memorize patterns. The result? A robust understanding of language structure and semantics. From translation to code generation, transformers power everything from chatbots to scientific research. Models like BERT, GPT, and T5 leverage these principles to achieve state-of-the-art performance. But the story doesn't end here. Researchers are now exploring sparse attention, efficient architectures, and even physics-informed transformers. The future? A world where AI doesn't just process language but truly understands it. So what's the takeaway? Transformers aren't just another model. They're a blueprint for building systems that grasp context, nuance, and meaning. By combining self-attention, positional encoding, and parallel processing, they've unlocked new frontiers in AI. If you're curious about the math behind it all, check the description for links to the original paper and deeper dives. Thanks for watching, stay curious, and keep exploring the cutting edge of machine learning.